So we continue. In the previous hour, we covered transformers encoder. You've seen the architecture of the encoder. Let me just put it again. And the encoder, as we've seen, is simply an input embedding with a position embedding integrated, summed up over the vectors, a self-attention block, and a decision block, which runs parallel with n different blocks. It was 6 in the original paper. Actually, this encoder part is implemented for many important industrial applications. Google search, Amazon search, use BERT features. I mean, they are complex as far as I understand. With my interviews with the engineers working there, I have friends. There are some hybrid architectures. And for example, Amazon search for customer search doesn't only use a transformer encoder based search. It uses that, but it uses some handcrafted conventional features as well. That's a bit difficult because when you're doing something in the industry, I had that experience, you don't use the best model. It's usually an ensemble of the best model with the simplest models you have, so that you try to, just cover your risks, because it's whatever. It's being widely used, and there's this model BERT, just like I said, BERT. Let me write it here. BERT, B-E-R-T, which is a model for NLP classification constructed on the transformer encoder, which I'm not going to be covering because it's too much into NLP. I just want this course to be a course of multimedia signals and multimedia processing because of our department. And if you're interested, there's always Tuğba course for details of transformer encoders and NLP applications. However, please note that then you might, but before I say that, you may ask then why we are covering the transformer if you are not into NLP, because the idea of transformers is being applied to vision and other multimedia signals as well, which I'm going to be showing in this lecture now. So that's why I strongly recommend BERT study. I strongly recommend those who are working on NLP to study BERT. With this knowledge of the transformer encoder, you'll easily understand it. Okay. Transformer decoder. Well, in the end of the encoder, you have features extracted from this sequence. The features include the position encoding, the interrelation between the words in multiple dimensions. So the transformer encoded the sequence, let's call it a language, using multidimensional attention. Kind of similarity dependent situation, you already know this. So it's not just a sequence of words with a history, that relation is actually the history that we call in RNNs. But it doesn't have to necessarily be history, because when if it's a time series signal, we can say that it's history, because a data coming after some data in a time series, that's the history information, because the dimension of time in a time series signal is unidimensional. I mean, it's before or it's after. However, in a language, it's not usually so. I mean, you can change the order of words. So that relation is complicated. That's why transformer uses this multi-dimensional dependence relation, self-attention to multi, because just like, when you change the words of a sentence in any language, you can still understand. Understood this, you have kind of the famous example, Yoda changing every word and looking very cool when he's doing that. That's the basic example of how you do it in a language. Okay, so imagine you change the order of the words, but still you have this high-level features at the end of the encoder. So what about the decoder? Well, it's not much complicated, but still you're going to see what it is. So the decoder part of the transformer contains 3 sublayers, guys, which is, let me get my pen, which is not working. So this part, and this part. I mean, this is the output part. So this is the sublayers. This is sublayer 1, sublayer 2, sublayer 3. This is the output embedding, and this is the decision part. And there's a feedback with me that I'm going to talk about it. So the first sublayer is masked multi-head self-attention, which is this part, guys. What you have here is you have the decoder hidden states applied into self-attention. What is decoder hidden states is you have the output coming from here to here and being fed back. So it is like you are creating the words, right? So unlike encoder part, the decoder part has some sort of feedback. Okay, this sublayer is very similar to the first sublayer of the encoder, but with the difference that the input representations are masked in such a way to compute the output representations at a given position. The sublayer can rely only on current and previous positions. So what we do here is we just get the current output of the decoder. Think of this as the hidden state of the decoder in the recurrent decoder model. Then you are calculating a self-attention, but you are masking some of them. It is like you are taking into consideration only some parts of the decoder output, which is like for the first sentences, the first part is taken into consideration for the first part of the decoder output. For the last part of the decoder output, it is the last part. And remember that this is always a 512 token vector. So it is like at the first run, it's an empty 512 token embedding. In the first run, the first token is not masked, but the rest is masked. And you're creating those words. As you do this, the sentence is created. But when you're doing that, you're adding position encoding as well. Okay? So just you're feeding the output shifted right. And again, position encoding. So that while this guy is processing the output, it doesn't forget where each token was that it created. Then add no, again, a residual connection, additional no. Then the output of this guy is used to calculate an encoder-decoder attention, which is the second block. It is like you're calculating the decoder hidden states relation to the encoder hidden states relation using this attention block. So it is not self-attention, but just like the calculations are the same, but the vectors you use are not the vectors themselves. One coming from the decoder, one coming from the encoder. So by using query, key, and value matrices, you are calculating the relations between the encoder hidden state and the decoder hidden state, if we call them hidden states. Then a residual connection, and normalization. And finally, the final sublayer is fully connected feed-forward neural network. So for that matter, it's quite similar. So this part is just like this part, but before that we have another one. So the idea is actually simple for that matter. We are using attention and some feed-forward neural networks. And the name of the paper is All You Need Is Attention. I don't have to tell you. That's a short for saying all you need is attention, but you also need some good embedding and position encoding. They didn't want to say. And in the end, with a linear layer and a softmax, you get the output probabilities, which word to choose. But that's the decoder idea. And as you can see, self-attention feed forward, self-attention encoder, decoder attention feed forward. So it's kind of attention-based encoder-decoder model. I mean, this is a simple way of putting it. Okay, so what are its applications? As you saw, I didn't just spend much time on the decoder part because I believe that it's related to more NLP. I'm going to spend time on vision transformer. So I'm quickly passing the decoder part. If you're interested, you can always study it. What are its applications? There are many applications which uses only the decoder part, only the encoder part, or we're using both the encoder and decoder part. For example, encoder-decoder based is language translation. Today, Google Translate is using the transformer. I mean, that was why the transformer was proposed in the first place. Or in the chatbots, and they are using transformers as well. There are decoder-based ones, just like the GPT. So the article you have seen on The Guardian in the previous lecture, mid-hour, was done on an architecture which is based on a decoder, which was then designed and changed to be a generative model. And there are many applications of encoder-based, just like the BERTs, which is the bidirectional encoder representations from transformers. The name is quite simple. It's a very high-level sentence representation, and it's that Google uses today, Amazon uses today. So the original transformer was proposed for natural language processing, and each part of the transformer has already many applications. Like transformers is kind of something old because it was October 2017, the first preprint. So it's almost more than 4 years now. In these 4 years, it is highly integrated to the industry already. Okay, that was all I was going to say about the first transformer. Rasmani's attention is all you need. In these 4 years, I mean, there were countless transformer papers, countless thousands of them. Everybody got mad about transformers. It was, since it was a breakthrough, just like Jeffrey Hinton puts it, people went crazy. I mean, just like after AlexNet, people went crazy about convolutional neural networks. After Vaswani's transformers, people went crazy about transformers. But this time, just to let you know, transformers require a very high level of computation. That's why not everybody can get crazy about it, because about AlexNet, you can get crazy on your laptop without a GPU, but with transformers, that's not the case. You definitely need extreme computation. Whatever, still people all around the world, institutions, academic laboratories, or industrial labs, they have the power of computation, and they went crazy. And one of the important applications were vision. I mean, when transformers came out like 4 years ago, the moment it came out, people started this question: can it be applied to vision? And it was so, I mean, the question was so controversial. People saying, yes, definitely it's going to be. Other people saying, no, it cannot be. That's natural language processing. But in the end, in 2020, last year, in October again, the K paper called The Vision Transformers came out. It was just like AlexNet or VGG or ResidualNet, an ImageNet classification network, the Vision Transformer. And it got the best results. So it was the proof that the transformer architecture, which is only based on attention, can be applied to vision as well. And you don't have to use convolutional neural networks with it, because before vision transformers, and I mean, the first transformer coming out in 2017, vision transformer coming out 3 years after, 2020, and during this time, in 3 years, people were trying to solve that question and trying to get an answer for it. Can transformers be applied to vision? And what people did was they were using it with convolutional neural networks. But vision transformers came out with this answer using only the transformer architecture, no convolutional neural networks. Okay. So in vision, attention was previously either applied in convolutional neural networks and convolution, or used to replace certain components of convolutional networks while keeping their overall structure. So let's remember what was the recurrent model of visual attention. So vision transformers applied this new context-based attention idea to vision. Okay, but before that, what was the idea? It was the visual attention idea. Because while people were trying to find a solution to vision transformers, people were in parallel working on applying attention to vision as well. So let's go over what they did. I mean, we have already done it the previous week. Remember the show attendant? I'm going to mention it again today, but people have done a lot of work on that. So what is attention in vision? Just like we discussed previously, attention is a difficult term to explicitly define in vision literature. Because in vision, we don't necessarily talk about sequences. We first have to understand what is meant by a sequence when it comes to attention. Okay? I mean, broadly speaking, it applies to a mechanism by which a network can weight features of level of importance to a task and use this weighting to help achieve this task. It was the previous week, remember, we used the word focus, the human cognitive ability to choose what is important and what is not important was attention. So it's the same. So it's applying that visually. Attention models are widespread among multiple areas of deep learning, and the learned weighting schemes, different schemes, can apply to features as diverse as pixels in an image, words in a sentence, nodes in a graph, or even points in a three-point cloud. So attention is applied to all kinds of data, and all kinds of these different modalities of data promise different things. I mean, applying it in graphs, which I'll be working on for the next 6 months, actually, we have a project on that. It's also exciting because a graph is usually a representation of a structural data. I mean, the relations of people in a Facebook. If you can define a certain attention idea, you'll be able to focus on a certain level of high-level information, right? Okay, how to do it in vision? The idea of attention comes from cognitive science. And actually, in cognitive science, people have been doing things about visual attention already. I mean, in this course, we've talked about attention as a part of artificial intelligence so that we don't, get confused. What was it? The first was the Badano's attention, which is a relation between the hidden states of the decoder to the encoder. And why we did this was to handle the complicated dependency that ranges far beyond the last sequence element C. That was the idea. This kind of dependency is also important in computer vision tasks, where instead of the dependency being along the sentence dimension, time dimension, but in the spatial dimension. Is this part of the image related to this part of the image? Kind of. Okay, the same texture may be present in multiple areas of an image. And multiple disjoint semantic cues may give clues to the overall classification of an image, for example. And remember, we've talked about this idea in recurrent model of attention. We could model the way we see images as glimpses over the image. Actually, this idea was also studied in vision. So I want to visit this idea before I get to vision transformers, because I don't want you to think that vision transformers was the only application of the idea of attention to vision. There were other applications, which was the recurrent model of visual attention, another famous Google paper. I'm going to just talk about it first, then I'm going to jump to vision transformers, okay? So the first one I'm going to talk about, the recurrent model of visual attention, was again by Google. I mean, everything is mostly by Google these days. But I'm going to talk about the paper which is not by Google, which is about Microsoft China, just like residual nets. Just bear with me, wait for it. So this is recurrent model of visual attention. So he's Alex Graves, famous guy, and Koray Kavukçoğlu, another famous guy from Google DeepMind. Recurrent models of visual attention. These guys in this paper talk about how we can model our visual ability to scan images using recurrent models. Because just like I said, we take glimpse on an image when we are modeling that image in our heads. Because in the end, when you're doing an attention mechanism, and you're applying an attention mechanism, you are constructing the context vector. Remember the context vector that we have been calculating the previous week. The previous week you're studying models of attention, and we always come up in the end with a context vector. So what we do is, as humans, we just look at an image, see shoes, foot, head, blah, blah, we jump. And in the end, after each jump, we update the context vector of that image, and we have the context vector. And it's actually already proven with some tools called eye trackers. You can record the eye movements of a person, and with some specific calibrations of that eye tracker with the person standing in front of the screen, you can actually record what glimpses that person make over an image. And these guys exactly try to replicate that model. So you have a human in your eyes, you have called some retina, and this retina, it makes a glimpse. And they try to implement this glimpse idea with a so-called glimpse sensor, which is a part of a recurrent neural network, which they call the glimpse network. So the idea is to allow the network to take a glance at the image around a given location called a glimpse. And that's what glimpse means in English. Then extract and resize the glimpse into various scales of image crops because in your head, you automatically do some multi-scale processing. You may remember this from the introductory level deep learning course. That's your ability to handle multi-scale operations. Your visual cortex in the back of your head can do this. So you just combine these and you just create that part of the model. And that's the glimpse vector, they call it. For example, the glimpse in the above example contains 3 different scales, and each scale has the same resolution. So just they resample it to same resolution, and you get there's a question. Okay, somebody's asking for permission. Of course you can. So they create this vector. So in summary, glimpse sensor is a kind of a retina-like representation of the image around a given location. So this is this is the kind of information you keep in the back of your head after you take a glimpse in a part of a scene. Okay? Then there comes the jumps with the glimpse network. Glimpse network is wrapped around the glimpse sensor, so it is deeper in your head. So you take a full-sized image and a location, then extract the retina representations of the image via glimpse sensor, then combine the extracted retina representations, that flatten is just mathematical, with the glimpse location using hidden layers and ReLU. So these hidden layers and ReLU, the recurrent neural network, decides which part to jump to, because it's a recurrent neural network. It's something it can do. I mean, I'm not getting into the very architectural details of it, but that's the idea. And in the end, is trained by reinforcement learning and other techniques with using the data of the eye trackers. It provides a prediction of how humans will look at this data. It's very important because you are designing a website, which parts will be seen, which part is seen, and what parts people jump into. That was the glimpse sensor. It's a way of modeling how people see the network, because it is trying to mimic the ability of humans taking a glimpse over an image. And this is actually the kind of attention people study. I mean, cognitive scientists, psychologues, people in the field of psychology study. And this was the glimpse network. So if you come across this recurrent model of visual attention, it is to model your eye movements over an image, okay? And that's also called attention. However, the type of attention we do in visual transformers is kind of different. But before that, let me get to another part of the visual attention. So this visual attention is mimicking human eye motion. The visual attention you've seen the previous week from show, attend, and tell was to relate the output to which part of the visual input, and to relate it to a part of the visual input. That's also called attention, because it is not, just like the previous example, not what humans focus, but it is what the output sequence is focusing at each sequence output to what part of the image to the part of the image it focuses. So the definition of visual attention changes in context. This is what people cognitive attention relates to. This is what the output of the word, the output word in image captioning relates to in the image. And so you remember this. So this is each word with relating to some part of the image. This is another type of attention. And in vision transformers, we have another concept of attention. I mean, the reason I'm trying to give you this perspective is when I was first studying attention in the last 2-3 years, I always was very confused about it. Everybody's talking about a kind of attention, but it's always different. Well, because nobody agrees on it. And the attention is very broadly, is the focus between a sequence element, the output sequence element to the input sequence element. And its definition depends on type of the problem and the context. So what is the definition of attention for vision transformers? Because vision transformers is, based on the transformer architecture, which is a trademark of attention. What is it? So vision transformers is inspired by the transformers. A tremendous success in natural language processing. People found a way to implement this to vision. What they did was classification, just like AlexNet or VGG. What they did was they split the image into patches, 16 by 16 patches. And using these patches as a sequence of patches in the spatial dimension, they fed it to a transformer. And the name of the paper is again, very nice, guys. And the paper is again from Google. An image is worth 16 by 16 words. You know what they say, an image is worth 1,000 words. When you get patches from the image, just like this, and you construct a sequence of these patches, and you feed them to transformer, which is originally used to process words tokens, these patches becomes words, and the title makes sense. An image is worth 16 by 16 words. Transformers for image recognition at high scale. Scale means using very large scale data. They use ImageNet, etc. So this is the figure 1 from the paper. If you just check the paper and you see figure 1, it is the model every almost every deep learning study has a figure 1 which explains their architecture. It consists of only encoder, guys. This is the transformer encoder. They do their own embedding type, which I'm going to be talking about. And the encoder is fed to a linear layer, fully connected layer, with a softmax here. And it makes the ImageNet classification, 1,000 categories, if the strength by ImageNet. So it's strength with many architectures. You see, CFAR 100, which has 100 categories, or VTAP, different training, they try and they present results. This is the architecture. So you already know the transformer encoder and what it does. You just feed some embedded patches here, which are these here. It just calculates the self-attention, then calculates, just convolves those values with a linear layer. And you have some features, just like the BERT extracting features in NLP, it's extracting features from this guy. So how the embedding takes place? Since this is not a sentence, the embedding part is a bit different compared to the original transformer, which is processing sentences. Okay, so the first thing we should understand, maybe not the first, the only thing we should understand about vision transformer is how it does this embedding. Okay, let's do it. So there's a very nice website from this guy. The name is Understanding the Vision Transformer and Counting its Parameters. It goes over this problem. What are the parameters and what are the steps? I'm going to go over the embedding steps of the vision transformer. I think it is important. The first thing I did when this vision transformer came out like a year ago was this. I tried to understand the embedding strategy of the vision transformer, because the rest is the same. It's just like a block. There are a few changes compared to the original transformer encoder, but that's what we do. Why? Because in future, I might want to apply it to a different type of signal, for example, like for a graph or a time signal. I need to understand what they changed in embedding so that I would understand the requirements of a transformer embedding. I would understand the requirements of embedding for a transformer related to the signal nature. If in vision, I need to do embedding like this. And in NLP, I needed to do embedding like the previous one. Then in, for example, in earthquake signals, maybe I need different type of embedding. To understand what kind of an embedding I will need for a different type of signal, I should first understand the handcrafted strategy behind this embedding, right? So we'll cover this part. Okay. So read the website, it's very nice. I'm going to go over it one by one so that you will have a solid idea of what there is in it. So in the first step, input of a shape of height, width, and channels. Why I say height, width, and channels? Because it's an RGB image, there's 3-channel image, and there are patches. It is embedded to n+1 D signals. D here being 256 because it's 16 by 16 patches. So it's 16 by 16, 256 D size, and is the number of patches. So if you have, for example, in ImageNet, let me get my pen. In ImageNet, the resolution is 224 by 224. So when you get 16 by 16 patches, you have 400 by 14 patches in it, which makes 196, which is n in this case. So n in this case. So what I'm trying to say is here it is n+1, 160, 97, 96, 97. Why there's +1, I'm going to talk about. Okay. So the image is split into n square patches. For ImageNet, it is 196 with a shape of 16 by 16 by channel RGB3, so 16 by 16 by 3, where P is a predefined parameter, which is 16 in the original paper. The patches are flattened, which means you make them a single vector, which is 16 by 16 by 3, something, I don't know, 800 something, you just calculate it. And you have n of them. Okay, the first step. So you have n flat patches, each representing an image. What you do is, you first do an embedding. You know what an embedding is, because 2 weeks ago we just saw that embedding is just like a linear layer, where you just calculate some weights. Since it's a linear layer with some weights, it's trainable, and it's being learned during training. Okay? Then this is the magical part. So just what you obtain is you don't change the size of it, because this was n patches and p times c length data, n times, let's call it d. That may be the d dimensions, d. And b is the number of batches, because in training you feed multiple batches. You feed a column in this dimension here. So you had n patches. You add something like one more. And when you're doing this, there's a weight vector here. You are in training. This is a bit strange and magical. What you are feeding here from here, because there's a linear layer here. There's a linear layer here. There are some weights here. What is the input? The input is a random vector. This is very strange, guys. I know. So what you're doing is, in both training and testing, you are feeding a random value here. Why are you doing it? Doing this is, you are creating, so you have n patches. You are adding one more patch, which doesn't have necessarily a value. This random patch will be the dimension where all the information will be aggregated over. This idea, this is called class tokens, guys, is prepended to the sequence. It's added to the sequence of the patch embeddings. The idea of this token is from the Bird paper. This is an idea coming from the Bird. Whenever you do a classification using the transformer encoder, that's a good idea, because Bird paper is the first paper that used only the transformer encoder to create a classification paper. So it is like vision transformer is not exactly applying transformers to vision, but it is more like applying the birth into vision, okay? Where only the last representation corresponding to this token is fed to. So what you do is you feed a virtual patch there, and patches, and you random patch. When this data is fed to the network, all the information of the patches will be somehow aggregated to this dimension, because in the end, we'll be using only this dimension to classify. So the loss function's gradient will fall over this dimension. The class token is a magical idea used in BERT, and it's very efficient and it's very powerful. It's being applied to vision. So this is the class token idea, okay? So that's why in the end, you're going to see, I'm just going to tell you something that I should be telling in the end, but I'm going to tell now. In the end, when you are doing classification, at the last step in vision transformers, MLP head, the encoder will have an output. We're not going to use the entire output. We are going to use the first column. When I first tried working on the transformer code, I was very confused. I just didn't understand why it was not using it. Then I realized that it was the class token and an idea coming from BERT. Okay, I'm not going into the very details of it, but that's the idea. Then you had this. There comes the positional embedding, okay? You just feed them to position. Positional embedding is the embedding that you already know of. The sine wave integration, just like a FM modulation. And in actually telecommunications, a multi-dimensional modulation is something very trivial. So instead of one-dimensional sine waves, you are feeding two-dimensional sine waves, which look something like this in the frequency domain. You are feeding them to positions. Again, you are frequency modulating the signal so that the positions of the patches will be somehow represented within the signal. And these are the patched embeddings. They are being fed to the transformer. So this is the strategy used. The class tokens with two-dimensional patch embeddings. Splitting them, nothing else. If you ever find a vision transformer implementation, there's an implementation in PyTorch, but there's this Hugging Face, famous library, open source library where everybody uses their vision, where everybody gets their transformer implementations. You can, if you go over them, you'll easily see each step in the code. So when pre-trained on large amounts of data and transferred into multiple mid-size or small image recognition benchmarks, VIT attains excellent results compared to the state of the art. So it performed better than the state of the art. It is worth noting that throughout extensive studies in the original paper, vision transformer only outperforms CNNs when the pre-trained data set reaches a very large scale. This is very important, guys. Transformers requires very large scale data, or they will overfit and will be unsuccessful. So everybody talks about in the internet. I saw these people, YouTubers, like AI YouTubers, convolutional neural networks are dead. Everybody is going to use transformers. No, guys, no. In very small networks, we still get use of convolutional neural networks. And when the data is not large scale, you cannot use transformers. Hence, it is less preferred to self-train. If your computational resources are fairly limited and you don't have much of a large scale problem. And these are the results. They have very good results in large scale tests. So you have the patch embeddings being fed to the transformer, and then the last column being fed to a linear layer, softmax, and some classification. That's the vision transformer. And these are the results. So basically, that's it. Are there any important studies about vision transformers? Yes, there is. I couldn't put it this year, but there's this SWIN transformer, guys, which is ICCB best paper in 2012. in October. So it is like weeks before today. And they are nice. I've watched this one. This girl is I could regulate it here. She explains nice things, and I should have comments. Yes, please find my comments. Just watch it. The swing transformer is. Let me get the paper. I think if you're interested in applying transformers into vision, swing transformer, swing transformer, vision transformer using shifted windows. It is applying the convolution idea, shifting windows idea, to transformers in more detail, and it's Microsoft Research Asia, because after residual nets, this is the first time they did something considerable compared to Google and Facebook, and they get very good results. And it was the best paper in ICC 2021. So most probably next time I'm lecturing this course, I'm going to be preparing this one as well. But I couldn't for this year. Please go over this. This is important. A study problem. And I think that's it. That's kind of enough for transformers. If you have any questions.